Good morning. This is Unlock Circuits 18 EC42, Module 3, Lecture 1, Part 5. We are discussing about the feedback amplifiers. Now, today we will discuss in particular about the shunt-shunt feedback topologies, having already discussed the uh, series shunt and series feedback topologies. I am Dr. Nurullah Sharif, C. Professor and HOD, CEC Cabin Institute of Engineering and Technology, Hyderabad. So the shunt-shunt feedback topology will consist of the figure over here, and at the output, what we have is the V naught. At the input side, we have what is known as II here. So V naught by II will give us a resistance, and that corresponds to the basic amplifier, which is a trans resistance amplifier. And the feedback network is going to take the output V naught, that is beta V naught will be equal to IF. IF will be equal to beta V naught, so beta will be equal to V naught by IF. And that will give us the the feedback network, which is resistive in nature. What you call beta will be equal to IF by V naught. So beta network will be what you call conductive in nature. So it will be a transconductance. So what we have is the voltage. What we have here is the current mixing, and what we have here is the what we have here is the current mixing, and what we have here is the voltage sampling. We are taking out the voltage here and feeding it as a current. So therefore, here we will have Is is equal to II plus IF, or II is equal to Is minus IF. And in the same way, we output is just taken out directly from here. Output is taken directly from here. So RL will be coming in parallel with this, and RS also. So here we are taking a source current source IS. That is the Norton's equivalent we are taking here. And that is because the input fed is IF, and therefore II will be equal to IS minus IF, or IS will be equal to II plus IF. So now what we are trying to do is we are trying to replace the output side by the so to say Thevenin's equivalent, and the this is a current dependent voltage source. This is a current dependent voltage source. This is voltage source which is dependent upon the input current, which is II. So that is AII. So the value of AII in case R naught is equal to 0 will be equal to the value of A will be equal to what you call AII is equal to V naught. So therefore A will be equal to V naught by II. Considering that the amplification A will be V naught by I. Similarly, here what we are trying to do is we are just trying to replace the what you call network by the feedback network by just the beta V naught. So that is an ideal structure where we are not bothered about the RS and RL, and also we are not taking the other parts of the so to say feedback network. So A is a trans resistance gain, which is V naught by II. This will be the unit which is resistance. And beta is IF by V naught, which is the trans conductance correspondingly, and hence it is trans conductance because output by input. Then we have the all the other things as it is same. We again consider that the A is a unilateral open loop amplifier. This is a unilateral open loop amplifier, and similarly the beta transmits only from this side to this side, not from this side to this side. So beta is not going to load the A, that is the assumption which we have. So now the equivalent circuit for the whole of the feedback network with IS and the input resistances RIF and AF as the amplification and ROF as the output resistance with feedback. AF is the amplification with feedback, ROF as the output resistance. So AF will be equal to V naught by IS. Then the value of IS can always be written as I1, II plus IF, and IF can be written as beta V naught, and V naught can be written as AVI. So On the whole, if you substitute all that, we'll get A by 1 plus beta, which is the standard. Any circuit will have, any feedback network will have A by 1 plus A beta, A by 1 plus A beta. The input resistance with feedback RIF will be equal to VI by IS. VI is the voltage here by IS is the input resistance with feedback. So that will give II is equal to, if you go back to the circuit over here, VI will be equal to II into RI. VI will be equal to II into RI. And that is what is substituted in place of VI here. So we'll get II RI divided by IS. So that will be RI into II by IS. Now IS can always be replaced again as we discussed. IS is the sum of II and IF. IS is sum of II and IF. So the current entering here is the current entering the node. The current entering the node. This node is IS and leaving is II and IF. Therefore, IS is equal to II plus IF. And that can be replaced over here, and IF itself is beta V naught. IF is beta V naught, and that can be written here, and V naught is equal to II, and we'll get II common, and II cancel numerator and denominator. Therefore, we are left with RI by 1 plus A beta. So this gives us that the shunt mixing at the input side, the shunt mixing which we are having at the input side, this is shunt mixing which we have at the input side, reduces the input resistance by 1 plus A beta. So there's a reduction. So general form is, in terms of impedance, is ZIFS is equal to ZIS divided by 1 plus AS beta S. Then we go for measuring the output resistance. So the input is what we are considering the current source, and that we are equating equal to 0 by connecting a test source at the output to find out the output resistance. So to find the output resistance, what do? We connect a test source at the output, and we put IS equal to 0, that is open circuit the source current. So if you do that, then what is it we are going to get? This is the equivalent circuit at the output, VT, AVI, V0, and we can find the value of I. ROF is nothing but the resistance measuring here, and that will be VT by I. How do we find I? I is nothing but VT minus AII. That will be the voltage across R0 divided by R0 will give us the value of I. So I is equal to Vt minus Ai by R0, and the value of II itself is nothing but, we know that II here is, if Is is equal to II plus If, II will be equal to Is minus If, and Is itself we are considering it as 0. We are taking the Is value as 0. So therefore II will be equal to minus If, and that will be equal to minus beta V0. If is nothing but beta V0. So minus beta V0, that is V0 is now Vt, therefore it is minus beta Vt for Is equal to 0. We are considering Is equal to 0. So if you substitute that here, or overall I as minus beta Vt, then we are going to get this. And Vt you can take out common, and then we'll get 1 plus A beta here, and I you can take this side, R0 that side, 1 plus A beta here, and then you'll get RF is equal to Vt by I is equal to R0 by 1 plus A beta. So again, the voltage sampling feedback reduces the output resistance to 1 plus A beta. So we had voltage sampling here, and that is reducing the value of the output resistance from R0 to R0 by 1 plus A beta. That is R0 is divided by 1 plus A beta. General form is ZOFS, that is the impedance, is equal to ZOS divided by 1 plus A beta. That is the ideal situation. Practical situation is where we'll take both RS and RL, and as well the feedback network is replaced by a better equivalent circuit. So now RIF and ROF are the input and output resistance respectively. The RIF is going to come here. That will be the parallel combination of RS and RN. That means 1 by RF. RIF rather, 1 by RIF is equal to 1 by RS plus 1 by Rin. So therefore, the value of 1 by Rin will be equal to 1 by Rf minus 1 by Rs. So Rin will be equal to inverse of that, and that will give us this 1 by 1 by Rif minus 1 by Rs. Similarly, Rout will be the value which is there over here, and the ROF is here. ROF is here, from here to here. That means ROF is parallel combination of RL and Rout. So that is 1 by ROF is equal to 1 by Rout plus 1 by RL. And that will give us 1 by Rout is equal to 1 by ROF minus 1 by RL. And Rout will be inverse of that. That means 1 by ROF minus 1 by RL. So from this, we can just try to find out the RIF and ROF, which is the input and output resistance with feedback, including the RS and RL, including the RS and RL. So now what we try to do is we'll try to replace the feedback network by a Y parameter model. This is a Y parameter model. So Y11 is the resistance at the input side, and the Y12 and V2 is the what you call voltage dependent current source. Again, we have a Y21 I1 over here, Y21 I1 over here, and then this will be Y22. So this will be the Y21 I1. So thus we'll have a Y parameter model at this place. Y parameter model at this place. This is not I1 definitely. This should have been V1. Okay. So because Y11, Y12, Y21, Y22, all these are admittances, right? So when we talk that this is a current source, this should have been V1. Fine. That doesn't matter because however we are neglecting it. So now what we do is Y11 we lump with RS, or rather with the amplifier. Y11 we'll take it here, lump it with the basic amplifier, we take it here, and Y22 also we lump it with the amplifier, that is we put it parallel with the basic amplifier, and Y21 we will neglect. So that means Y21 V1 rather, Y21 V1 is the one which you are going to neglect. Okay, so once we neglect that, then we'll get an equivalent circuit which is of this type. So Y11 is lumped here, Y22 is lumped here, and only we are left with Y12 V2. So the value of IF is equal to Y12 V0. So Y12 will be equal to IF by V0. And in turn, that will be the same thing as I1 by V2 when V1 is equal to 0, which is the port 1 short circuited. So thus we will get here the the A circuit, the amplifier circuit is this over here with the summary of that will give you the input side is RS in parallel with R11, output side is R22 in parallel with RL, and this is the basic trans resistance amplifier. Then the feedback, when the R11 is obtained from the feedback resistance, and R11 is nothing but the output is shorted over here. R22 is the one which corresponds to input is shorted here, and the gain A is equal to V0 dash by II dash. The gain without feedback A is this much here, and beta is obtained by shorting the input side over here and connecting the voltage source at the output, and that will give us beta is equal to IF dash by V0 dash when V1 is equal to 0. So taking an example here of the shunt-shunt type, we need to determine the voltage gain, the input resistance, and the output resistance when beta is equal to 100 for this circuit. First, we need to do the DC analysis. When we do the DC analysis, then what we try to do is the input signal source is not there. Vs is not there. So this is connected to ground. So the equivalent circuit will become this now. The equivalent circuit will become this now. So then what will happen is there is a voltage here which is VBE, which is equal to 0.7. Once this is VBE, which is equal to 0.7, then the current flowing here, this also will be VBE because this is grounded. So whatever voltage is there between this point and the ground will be same thing at this point and the ground, because this point is common. Ground is also common. So VBE is appearing across 10 kilo ohm. So 0.7 by 10 kilo ohm will give me 0.07 milliampere. So that 0.07 milliampere is added with IB, and that is flowing over here. The current flowing here will be IB plus 0.07 if we consider IB as this current. Then this is the collector current, which is beta IB. So this is a transistor, and so this is the collector current, which is equal to beta IB. Now this current and this current together will flow over here, then we'll get correspondingly beta IB plus IB plus 0.07, and that is beta plus 1, IB plus 0.07. So now we can get the voltage at this point, VC. VC is nothing but the voltage across the 47 kilo ohms, and we'll come over here, right? The voltage across the 47 kilo ohms plus the voltage which is VBE, right? So the voltage across this is IB plus 0.07 multiplied by 47 plus the VBE, which is 0.7. That is what is written here. 0.7 plus IB plus 0.07 multiplied by 47. That will give us the value 3.99 plus 47 IB. Then we come to the current which is flowing here. The current which is flowing here is nothing but beta plus 1, IB plus 0.07, and that is written on the right hand side. And this current is nothing but on the left hand side we are writing the 12 volts minus the VC. 12 volts minus the VC divided by 4.7 kilo ohms, and that is what is written here. So the current flowing here is this voltage minus this voltage, which is VC divided by the resistance here, that is equal to the current over here. So we have two equations here with two unknowns, VC and IB, and we need to find that. So the best way to find would be from the first equation, we can get IB as VC minus 3.99 by 47, and that value can be substituted over here. VC minus 3.99 by IB, and we can solve that equation in VC, then we'll get 4.5 volts. So once having got this, then IB is again, we have written in the, by simplifying the first equation, we have written IB is equal to VC minus 3.99 by 47. So if you substitute the value of VC equal to 4.5 volts, we are going to get IB approximately as 0.015 milliamperes. And IC is nothing but beta IB. The collector current is nothing but beta IB, and hence beta is 100, and we are going to get the value which is 1.5 milliamperes. So having found IB, IC, and VC, which we are using the DC analysis, now we go for the small signal model. In the small signal model, we are replacing again at the input side by means of a current source in parallel with the what you call internal resistance RS, and this is a hybrid pi model of the transistor where we are writing R pi, across R pi will be V pi, and this will be a current source which is GMV pi. We are neglecting R naught over here. So if you want, we can consider R naught, but since R naught is not given, small R naught is not given in the what you call problem, we'll consider R naught to be, small R naught to be infinite. Small R naught to be infinite. Now we need to do the analysis for this. When we do the analysis, when we find the input resistance over here, when we want to find the input resistance over here, then what we do is we need to ground the output. So therefore RF will come in parallel with this. And when we, what you call, want to find the output resistance, then what we do is we just open the current source. So that means RF in series with this combination is going to come Might be that RF is much larger than RS in parallel with R5. Therefore, only RF is written over here. But ideally speaking, once this is not there, then we'll have RF divided by the RF plus RS in parallel with R5. RS in parallel with R5 might be very small compared to RF. That's why it might be neglected. However, the exact value for this should have been RF plus RS in parallel with R5. Fine. So having written the equivalent circuit over here, then we can try to find out the input resistance and output resistance, and also we can try to find the transfer gain. The V pi value is the voltage across this over here, which is nothing but II dash. That is equal to II dash is the current which is flowing here. The II dash is flowing here, multiplied by all the three resistors in parallel, is going to give us the value of the V pi. And V naught will be nothing but minus Gm V pi with RF in parallel with RC. So the current which is flowing here is like this. Through the RF and RC combination, the current will flow upward because current is going to flow like this, right? Current is going to flow like the direction of this current is like this. So naturally it should flow like this. So therefore V naught dash is minus Gm V pi, that the current value which is flowing there multiplied by the equivalent resistance of RF in parallel with RC. Thus we'll get this. And V pi we can substitute from here, and we will get the equation for the, once we substitute it here, then we'll get here minus Gm multiplied by this into II. And II dash, if we take it on this side, then we'll get A is equal to V naught dash by II is equal to Gm RF in parallel with RC multiplied by RS in parallel with RF plus R pi. And that will give us minus 358.7 kilo ohms. Similarly, the Ri value is just the parallel combination of all this, and we'll get it as this, and Ro is the parallel combination of these two, hence we'll get this value. Then we come to the beta network over here. Beta network is the V naught dash here and IF here. So therefore, beta is equal to IF dash by V naught dash. That will be equal to the minus 1 by RF. So IF is flowing like this. So IF is flowing like this over here. So therefore, beta will be equal to the IF dash by V naught dash. IF is in the reverse direction. Therefore, this will be minus 1 by RF is equal to minus 1 by 47 kilo ohms. So having written the value of beta, now we can determine the closed loop characteristics over here. So the gain multiplied by the value of beta A is minus 358, whatever we have got, 358.7, and the value of beta is minus 1 by 47, and all that is substitute over here, and we'll get this. So this quantity which is there here is 8.63, which will be very useful. 1 plus A beta is here, we have got 8.63. Then we have the what you call value of V naught by Vs. V naught by Vs is the voltage gain, whereas AF is V naught by Is. V naught by Vs will be equal to V naught by Is into Rs. V naught by Is we know. So that is minus 41.6 divided by 10. That will give us the voltage gain as minus 4.16 volt per volt. This is the voltage gain, whereas AF is the resistive value, trans resistance value. Now the input resistance with feedback will be RIF is equal to Ri by 1 plus A beta. Ri we know 1.4 kilo ohm divided by 8.63. That will give us 162.2. Similarly, output resistance with feedback for the shunt-shunt type of amplifier will be R0 divided by 1 plus A beta. That is 4.27, which we have found, divided by 8.63. That will give us 495 ohms. So with this, we come to the end of this lecture. Thank you.